All right, it's real quick. It's not that complicated. Then we'll take a break, and when you guys come back, we're going to do something a little bit new, and it's another kind of a big topic in waves that you guys are going to need to understand. So here, you can see an oscillation that's damping. All right, now I don't want you to get confused with the term dampening. Dampening is like when something is damp, it's kind of like wet or whatever. That's a different term. All right, that's not used here. This is really just damping. And most waves in real life will damp because there's friction and there's energy loss and things like that. If you have a spring attached to like, let's say a crossbar there, if I had a spring attached to it and I made it bob up and down, so it's oscillating up and down, eventually it would stop. It doesn't bob up and down forever. And the, the reason for that is because the mass is interacting with a medium that it's in. And what medium is that mass in? Air, right? It's air resistance is doing it, but it's air, really. All right. So if there was no air, if it was in total vacuum, then that thing would bob up and down forever. Again, that's if we ignore friction. So today we're ignoring friction, but we're not ignoring air resistance. All right. And it doesn't have to be just air. It could be any material that you want. It could be like liquid, right? So if this thing was oscillating up and down, right, it would be like in the water, let's say, there would be water resistance. If it was in oil, there'd be oil resistance. If it was in honey, there would be a honey resistance. And the bigger the viscosity of this material, this medium that it's in, the more damping is going to occur. You guys follow what I'm trying to say? So what do you like if I have to compare air and water, which one's going to cause the mass to stop oscillating first? Air or water? Water. Exactly. If I had to say like honey or uh, ethanol, which one would make it stop first? Okay. So there is a value, a property of the material that we need to consider, all right? And we're going to call that a very generic letter B, okay? And this, we're going to call this the viscosity of the medium. And every medium, other than, of course, vacuum, will have a viscosity. So we have to be able to add that to our equations that we learned already, but to add that to our equations so that we can now understand what calculates or predict how many oscillations it might make before it stops or before it's, we'll get to some examples. All right, any questions so far? We learned that angular frequency for, actually, before I talk about that, I want to point out this specific damped oscillation. This specific damped oscillation, you might not see it well from where you are or even on your screens, but there is a dotted line here. You guys see that dotted line? That is actually describable by a function, right? And if I were to just look at this top one here, what kind of function is that? What kind of function? Kind of an inverse proportion. I would call it more of like an exponential, a negative exponential function. All right, so it's exponentially decreasing. Does that line ever reach zero? In reality, yes. And in this example, no. All right. So if there was no regular friction, right, and it was just damping, it would still oscillate forever, except the oscillations would get smaller and smaller and smaller with respect to time. And again, this is what it looks like for this generic. If I had something really thick, like honey, let's say, what would this curve look like? Would it be steeper or less steep? What do you think might be what it looks like? If this oscillation, let's say, was in water, right, and now I'm trying to do the exact same experiment in honey, this is a curve for water, all right, this is water. What would the curve look like for honey? More what? more of a line, so you'd think it would be more like this. So would the amplitude decrease faster? Okay, so the amplitude would decrease faster, and you would have something like this. Let's say that's like something that's really, the amplitude is really decreasing really quickly. All right. All right. So we need to figure that out. It might not be obvious here, but the frequency, the angular frequency, whatever you want to call it, is also changing. The frequency is not it's not staying the same. So here, I might have a different frequency, or this might have a different period. This part of the oscillation might have a different period than this. So we need to find a way to describe that period as well. So there is an expression for it. And so we have, this is angular frequency when there is no damping, all right? No damping. We learned this as the square root of k over m. You guys remember this? And this is for obviously a mass spring system. It doesn't apply to pendulums yet. However, there is something called a damped frequency, angular frequency. So damped, which we're going to call this W prime, omega prime. All right? This is described by the square root of k over m minus b squared over 4m. All right? 4m squared, sorry. And you see how now we have this factor b, which describes the viscosity. So this is medium specific. It's specific of the medium that you're in. So far, so good? By the way, in case you're curious, which everyone should be, the units are kilograms per second. You don't need to hide your phone, I can see you do it. Okay, that's one thing. So now that's your omega prime, your new angular frequency for a damped system, and that's what it would look like. Now we need to describe the actual like wave part of the function, and there's two parts to it. Before we had that, the amplitude of my oscillation was just A, but now my amplitude is decreasing. If I go back, this is actually the function of amplitude, right? This line that I put is describing the decrease of amplitude with respect to time. So that means that there's an expression now for amplitude. So amplitude with respect to time is going to be a function that's time dependent. And of course, you're going to need the B to be involved in it. You have a question? The showing thing is what? That's weird. You're talking about Adobe Connect? Is it just your screen? No, actually, it does look like it here. So let me just. Is that better? Okay. All right. Okay, so what we came up with is that amplitude is also changing with respect to time. So this is a decreasing function. Amplitude is really decreasing. And it's a function of its original amplitude. And I think you guys, some of you will be familiar with this form of equation is initial amplitude multiplied by e to the power of negative b over 2m times t. Using this equation, you're able to find this line that I drew here, like 100 times over now. That line, the equation of that line, is described by this formula that I'm describing here. And you can see that B plays a role in it, right? And the higher B is, the more rapidly that amplitude is going to go down, right? That's that coefficient. If you guys remember your exponential laws when you were, I don't know when you learned this. When did you guys learn exponential laws? So if you remember back in high school, that coefficient there decreases the steepness or increases the steepness. Okay, that's that. But that doesn't also describe the actual wave function, which is ultimately what we want. So that's the culmination of this. Is that now if we want to describe the actual, if we want to describe the actual, like actual oscillations, the sinusoidal or the cosine function, we have a new amplitude, and this amplitude is described here. So it's going to be initial amplitude multiplied by the negative b over 2m times t. That's your amplitude multiplied by the cosine of your angular frequency times time. But it's not just any angular frequency, it's your angular frequency, your damped angular frequency. Justin. Oh. Yeah. Position. Like it's like remember we had it before x of t is a cosine omega t. This is the same f. It's really like where is it in this up and down space. There's no friction here. This is really just from the resistance of the medium. Okay, and that medium is described by B. Are there any questions on this? All right. Okay. Take a 5-minute break. Come back at 2:35, and we'll do one example of this, and then move on to something else. All right, so I just really quickly now in the last like 10 seconds came up with a question. I hope it works. Please don't get upset if it doesn't. It doesn't really matter. The point is that we understand how to apply this concept, all right? The question is, after how much time, yeah. What's the odds doing that thing again, yeah? Oh, you know what it is? I think I know what it is. I think it's because then every time I do the rotation, it kind of like throws it off. It's working now, right? Okay. Hopefully it doesn't happen again. Let me know if it does, all right? I'll fix it. All right. So the question is, after how many oscillations and how much time did the amplitude become 1/10 of its original amplitude? So that's like if we're thinking about a mass spring system, let's say I stretched it to 10 centimeters. If it was not damped, it would be 10 centimeters below the equilibrium, 10 centimeters above, 10 centimeters below, and it would just oscillate with this kind of pattern. Now what I'm asking is, after a certain amount of time, this 10 centimeter amplitude became a 1 centimeter amplitude, okay? Or 1/10 of its original one. So I'm asking you how much time passed for that to happen. So what you would do is you would look at your amplitude equation. So you know that the amplitude with respect to time is equal to your original amplitude multiplied by the factor that I told you guys about. This, all right? And what's that? Oh, and the times time, you're right, because we're solving for time. And we know that the original amplitude is 10 times more than the final amplitude. So if I were to just divide both sides by AO, what I would get is 0.1 or 1/10 is equal to e to the negative b over 2m times t. How would you solve this algebraically? Yeah, you take the natural log on both sides of the equation. So you'd say the ln of 0.1, and the what's the ln of e to the power of x? Ln of e to the power of x is just x. It's just the x, right? So if in this case, my x is whatever I drew in that bracket there, right? So ln of 0.1 is equal to negative b over 2m times t. Yeah. My b in this case is given to me, it's 18. My m is given to me as well, it's 0.5. So what I have is that the ln of 0.1 is equal to negative 18t. Right? Because 2 times 0.5 is just 1. That's pretty simple. And so therefore the ln of 0.1 divided by negative 18 is equal to t. It's going to give me a small number. Can someone tell me what that number is? I don't. I have my calculator, but I'm really lazy. Zero point. What are the units? Seconds, exactly. All right, so I figured out it takes 0.13 seconds for my oscillations to reach 1/10 of its original oscillation. So is this a really thick material or a relatively thin material? Pretty thick, right? It took almost just over 1/10 of a second for the amplitude to decrease 90%. That's pretty significantly fast, if you ask me. Now the other question is how many oscillations does this take? So now we can talk about angular frequency. So we know that our angular frequency is equal to the square root of k over m minus b squared over 4m squared. You have all the values. You have k, you have b, you have m. Solve what the angular frequency is. Hopefully it doesn't give you a negative number or an impossible answer. If it gives you an impossible answer, we'll just make something up because I didn't really choose my numbers carefully. It's going to give you an impossible answer, I'm pretty sure. Yeah. Okay. Did everyone get an impossible answer? Square root of a negative number? Did it work for you, Nora? What did you get? The mash ball. All right. That's because I didn't choose my numbers carefully. Now let's say I did, and the answer was 13. Just a random number, okay? What are the units for angular frequency again? Meters per second? Degrees or radians per second? Radians per second. All right. So if there's 13 radians per second, how many oscillations will it do in 0.13 seconds? So I can multiply them, right? So my angular frequency multiplied by my time is going to be 13 rads per second multiplied by 0.13 seconds. That'll give me some number. Could you guys calculate that for me? 1.69 units? Radians, exactly. Now, how many oscillations did it do? Did it even do one oscillation? How many radians is one full oscillation? 2 pi. Did I get 2 pi amount? No, I got close to 2, I guess. I have, let's do a fraction here. 1.69 over 6.28. This is just 2 pi. Can you guys tell me what that fraction is? 0.27. So it did 0.27 of a full rotation, roughly a quarter of a rotation. Okay, a quarter of a full oscillation. Did it reach the minimum? No, the minimum is after how many oscillations? 0.5, right? After half of an oscillation, it would reach the minimum. So it didn't even reach the minimum. Okay? Any questions on that? Yeah, I'll give you guys a chance to write this down. And you can open up the next PowerPoint. It's going to be called Waves on a String. I think it's number 4. Okay? Can you show me after class? Okay, for now's not the time. Okay. Okay, so we're good with this. What are you talking about, Daniel? Conversation. Okay, we're going to talk about waves on a string, and eventually we'll talk about really. That's the whole point of this whole thing, because it applies really, really, really well with guitar strings or any kind of string instruments, such as what kind of string instruments do you guys know? Who plays the guitar? Yeah, I asked this before. Who plays another string instrument, like the violin, the viola, cello? What do you play? The violin? Okay. Anyone play the ukulele? Yeah. I play guitar hero. That's pretty much the extent of my musical abilities. All right. So this concept really applies to strings. Okay, and well, we're talking about the speed of a wave on a string. And so you have to imagine that if Danielle and I held a string, actually I can do that because I have some string here. So if Danielle and I are holding a string, we're connected. And if I give it a little perturbation, right? Let's hold it tighter, right? try to do this. And not very good. Maybe a little bit looser. Okay, that is maybe a bit more obvious now. If I were to do this, my wave is traveling, my perturbation is traveling from my end to Danielle's, right? And eventually I can oscillate this in such a way. Let me see if I can do it. Yeah. Okay, if we go like this, and if I go really, really, really fast, I gotta do it the same rate. I can't do it. I almost hit her in the eye. If you do it really fast, if you closer together, you're gonna have to do it even faster. You gotta like super fast, like faster, like even faster than that, like super fast. No. In fact, you need like a drill to be able to do it. The point is that the faster you spin it, it's gonna reach this point where you're gonna get to something called a fundamental. And the idea of fundamental frequencies is very prominent in string instruments, right? Because you pluck a chord and you'll get a fundamental frequency that's going to produce a sound that's equivalent to a note. And depending on how many like artificial, like you can put your fingers in the frets, and you guys know what the fret of an instrument is, like where you put your fingers in the guitar and the violin or any kind of instrument. Based on where you put your fingers, you're going to create something called a node. And that node is going to make it so that your frequency changes. That creates different stuff. We're going to learn all about that. It sounds kind of weird, but I'm like, this is like the physics of music. That's right. Science is even ruining music for you. All right. So let's get started on that. We're going to talk about the speed of a wave and all that stuff. We're going to talk about something called standing waves, which is, in my opinion, like the most interesting part of this wave section of the course. We have a speed of a wave. That's really just the the amount of time it takes to, or how fast the energy goes from one end of the string to the other end of the string. We talked a little bit about that. You guys remember what the variables were for this? Like what determines how fast the wave goes on a string? I showed you the equation. We didn't really talk about it too much, but I did show it to you guys. You guys remember what it was? Yeah? Yeah, exactly. So there was two or arguably three different things that mattered. One was the tension of the string, the force, right? And the second thing was the mass length density, so how heavy your string was with the string. That's what I mean by the property materials of the string. And and so we're talking about a string now, but we need to know that the material itself determines what the how fast the wave goes through it. For example, like sound. Sound travels faster in water than it does than in air. Did you guys ever hear these YouTube people called slow mo guys? Their videos are like hypnotic and addictive to watch. Basically, they just do I would argue how scientific it is because I think they're just stupid people. They do like scientific things and measure it in like slow motion. And what they did is they detonated a grenade underwater and looked at it in super slow motion. Very cool to watch. I encourage you to watch it just because it's just fascinating. But you can clearly see the wave in the water travels way faster than that same grenade um, in the air. I think the experiment that they were trying to I guess to prove or disprove was that it's safe to hide from a grenade underwater. And the answer that they came up with was no, absolutely not. If the grenade is underwater, you need to get out of the water. Okay. Any questions on grenades? Just because I'm Middle Eastern doesn't mean I know a lot about this stuff. All right. So, in any case, we're talking about the speed of a wave and all that. Okay. So we got this, there's a derivation for it. I'm not going to take you guys through it because it has to do with the tension force and there's going to be a lot of derivations, a lot of derivatives to do, and I don't want to get you guys into that. But essentially what you come out with is that the velocity, the velocity of the wave on a string is equal to the square root of the tension force divided by mu. And mu is this mass per length density of the, yeah, very important too. And what I'm talking about this velocity here, right? What I'm talking about is how long it takes or how fast it takes for the energy to travel from one end to the other. I'm not talking about the how fast a particle moves up and down in that wave, okay? It really is the propagation of the wave, how fast the wave propagates through the string. So this is the propagation wave, okay? Propagation speed, rather. Right? I would imagine it's faster because the pressure increases the density of the water. So the higher the density of the water, or the higher the density of the material, the faster the wave will propagate. It doesn't have to just be water. I'm just gonna skip through this. Essentially, the reason why you have a propagation of a wave is, if I were to pause me doing that little lash whip thing with Danielle holding it at the other end, is if I make this part go up, then this particle, let me guys see it, or should I switch colors? This particle here, this particle here is going to provide a tension in this direction. And that's going to make the next particle next to it move upwards. And this one's going to make the next particle move upwards, move upwards, move upwards. So essentially, it's always going to take this chain reaction of like string particles moving the next particle up. And that's why you have a propagation of the wave. The particle itself is not moving along the x-axis. It really is just the energy. And that's all you need. So we know that the stronger the tension, the faster the wave, and you saw that that equation. I want to show you guys that right now. So this is so here I call this the mass unit length, but in fact it's we substitute that with this symbol mu. The derivation, click on that link, not right now. Those of you who know me will predict who is giving this video. There's like one of three people who I like idealize for their explanations on physics explanation. You'll click on that and be like, that's so cat. All right. We're going to talk about standing waves, but we need to talk about something called interference and constructive interference and destructive interference. I'm going to talk about it very briefly now, but I want you guys to do kind of an experiment. Let's see what it says here because I don't want to go in out of order. Okay, so here I'm talking about the guitar strings, and here I have the table for the mass length density. So the mu, this is mu, and this is the tension. And on a guitar, if you have this tension and this mass, this kind of string, right, then you're going to produce these notes. And those of you who are well versed in music, you know, like your A notes, your B notes, that's what they represent. Okay? So we'll produce some predictable frequencies. We're going to be able to calculate that soon. And based on that, you got this speed on the string. And then now what we need to do is talk about nodes and antinodes and things like that. And that all fits under the umbrella of a subject called standing waves. I want you guys to do this. There's half an hour left. I think you guys have more than enough time. There is a lab on Moodle that I just uploaded this morning called a virtual lab for string waves or something like that. I want you guys to open that up. There's going to be a link. I want you to click on it. It might ask you to update your Java. Do so, and then try to run this application. It's pretty cool. It's very simple, but it's very elegant the way it's designed, and it really helps you understand. I need you guys to understand this to be able to move on to the next thing. So go ahead and do that. Half an hour is plenty of time. I will end with this. Okay? Andre, what's up?